Okay, we're going to do devices now. This is the last major section before the midterm, so we're coming up on that. We're actually making pretty good time because I can throw a whole bunch at you at the same time, so I'm sorry about that. Um, I just added some essay questions. I said in the last video I was going to throw them out there for wiring. So read and do the questions at the end of 3, and then some essay questions, which I'm sure you're going to absolutely hate, but it'll get you to think about it. And if you can't answer it, I mean, this gives me a time to give feedback and clarification, and give me your best shot. And if you have questions about, I understand this and this, I'm not exactly sure how this works, let me know that and I'll respond, and we'll kind of firm that up. So understanding those things are really good. The memorization things that we'd have so far, oh shoot, I remember, just remembered, we'll do that when we do the review. We actually have a table of all the different all the different wiring types and the connectors for them, and the maximum cable length and the throughput. Basically all the content of all the quizzes that we would normally have had if we were in the classroom, that we're missing out on. So I'll review that as we go through. So we're losing points for that, but I'm making up for those points by doing other things that we normally wouldn't do, like the essay questions and stuff like that. So you'll just have to, especially those who are going to take the Net Plus, you're going to have to pay attention to this section we're reviewing for the midterm on the things you're going to have to memorize for both the midterm and for the Net Plus. Okay, moving on, we're going to talk about LAN connectivity, and I'm going to flip back and forth between that and, well, there's nothing there now, but we're going to do our OSI layers again. I'll build those. Well, I guess you can, not that you care to watch me really, but we're going to do layer 1, layer 2, and layer 3. So we're going to talk about the different devices that are at those 3 layers and what they do and why. This is, I like this lecture because it starts to kind of cement some things together, and you start to have some aha moments if you haven't had those already. But the big thing we're going to talk about when we talk about all this is we're going to talk about the rules and the way that the devices actually handle traffic. That's probably the most important thing in all this. Okay, so and every device at every layer can do everything at its layer and below. So all the layer 1 devices are the same. The layer 2 devices can do 1 and 2, and 3 can do 1, 2, and 3. So as we're building up, there's a lot of repetition. Repeaters, join segments of a LAN, we know that. They work to regen and send. Works at layer 1 because repeaters and hubs can't, because they're at layer 1, they can't see any of the addressing for the MAC or the IP of the port, so they don't have the ability to filter. They just bucket passing, they just regen and send. So that was the bucket passing coming from the pond to the fire, water, empty bucket, grass, kittens kind of thing. We don't alter the packet or the header info because there's no header info or trailer info at layer 1 to do anything with. It doesn't direct or filter traffic because it doesn't have any addresses. Like I said, it doesn't have the MAC or the IP, can't see any of those. We can do translations between types, and we were just looking in the last video at a Cat5 to fiber to ST, I believe, a transceiver, as it was called. The network card actually is a transceiver as well, but this was that little rectangular box, the $100 transceiver that we were talking about using because we needed to use a fiber run. Any cross connect between any type of physical cabling, so connectors or fiber types or cable types or anything like that would all be layer 1, and repeaters can do that. So a repeater could have an RJ45 on one side and fiber on the other. In fact, the transceiver that we just looked at would do that. It would actually regen because it would plug into the wall, so it would actually regen. So it would be functioning as a transceiver and a repeater at the same time. we get longer runs using a repeater, and we talked about hubs before. We have not talked about managed. The one switch we looked at last video or the video before was an unmanaged switch, that little $18 gigabit 8-port switch. Unmanaged just means I don't have any evaluation of anything. Managed would be that it usually will have a web interface, and it has the ability to track how many bad packets, how many broadcasts, how many unicasts, how many multicasts. I would usually on a managed would then be able to do configure my ports. I could configure speeds. Usually there's a lot of different configuration we could do there. We could actually set up VLANs as well. We haven't talked about VLANs yet, but I could do all that on a managed switch. When someone says, hey, and we're talking about repeaters, I wouldn't have a managed repeater, it would be a managed switch. So this goes all the way up the stack. But when someone says, hey, what's the difference between an unmanaged and a managed switch? And my follow-up question is, how many ports? 24 port. What's the difference between a 24 port managed switch versus a 24 port unmanaged switch? And I would say probably the difference between 50 to 75 on the unmanaged and 300 to 1,000 on the managed. So you're getting a device that actually has a computer embedded in it, and you have a lot more configuration, and you can get a lot more stats out of it and do a lot more with it. As usually that would not be you would not have a managed layer 1 device. That would be stupid because there's nothing to manage at that point. But I've stuck it here awkwardly just so we can get going with that. Okay, so back to our layer 1, and I could write all this out. So we had the cable and the connectors and blah 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 blah. But the rules that we have, and these are my rules that I came up with when I was studying for the Net Plus. So here we had a repeater and a multi-port repeater. So all they're doing is taking that signal, and they are regenerating it back to 100% at whatever it was. Hopefully we didn't have attenuation to the point where we're below the noise floor, because it will regenerate garbage back to 100% and send it on and we'll have errors, which is again why we have maximum cable length, so we don't have and usually we want to stay well within that. Modern cable probably could go to 400 feet and would be good. I tend to stick 250 or below. If we're going to be above 250, I'm going to think about what are some other options that we have. Do I want to move the switch? Can I physically move the switch to a different location and get 250 runs going either direction instead of having one long run? So a lot of other things that we think about when we do that. All right, moving on to layer 2. Layer 2 was a bridge, or a multi-port bridge, which is a switch, and almost all of our interactions early on, at least, are going to be with switches. The only bridges you're probably going to use will be switches that are managed, that are actually being used as a bridge. It's pretty rare that you can use a repeater or a hub unless it's in a very specific where I need to have a repeater that's in the middle of a line. But even at that, that $18 gigabit switch, the gigabit switch, for less than $20 you could throw that in there and that works as a repeater. I mean, it does all that plus. So if you just needed extra cabling, you could throw that in the ceiling somewhere, and you'd be good. The only other thing would be maybe having that be PoE, but I haven't seen a PoE installation with a repeater. I don't even know if that's possible. That's a good question. Not important enough to look it up right now, but that's a good question. All right, so bridges are at layer 2, so they have the MAC and LLC sublayers that we talked about before. It can read and edit anything in layer 2. It has the ability to see protocols, so it can link segments. It has the ability to see, I said that wrong. It has the ability to see topologies was what I meant. And so it can change topologies it has to use the same protocol because protocols are going to be at layers 3 and 4. So since it can't see it, they have to be the same protocol. It can't change that. It can see topologies, and so it would be able to bridge, which is why it came up with its name. It would be able to bridge two different, star Ethernet and token ring if we needed to. It can filter direct traffic based on MAC. It says destination address there, but it's actually MAC. It will build this learning filtering bridging table. I have seen books and heard people say that bridges will have a internal routing table, which makes me cringe because routing table implies layer 3 and IP address, and a bridge definitely does not work at layer 3 and does not have an IP address available to it. So I like learning table myself. Filtering table is okay. I'll also do bridging table. So usually learning or bridging table is what I'll use, which says this has a MAC by saying bridging table. It has a MAC address in it, so it can identify all the different ports and the machines connected to those ports via the MAC address, and then it can either pass traffic or not pass traffic based on that MAC address. Now, that being said, we've got a couple different things. We've got two bridging methods. We've got some switch modes down here and bridging methods. These get a little bit confusing because they sound kind of similar. So I'm going to go through, and this is the biggest part of the. Oh my God! I've just been pointing to the screen down here and not up here. Okay, so we did regen and send, and then we went, let me run through this real quick. Works the data link layer, regenerates link segments using the same protocol because it can't see the protocols because they're higher up. The topologies aren't even on this list. Can filter and direct traffic, builds a learning filtering bridging table. We were just talking about that. Okay, so bridging methods, and we had switch modes, which are down here, cut through and store and forward, but right now we're using a transparent and source route bridging. And then I went to switch back to the document camera and remembered, see, I'm concentrating on what I'm looking at and not looking at the preview screen that you're looking at. Eventually, we get all done with summer, and I'm actually going to get the hang of this, and I'll understand how all this works. Okay, so I'm going to temporarily, because we're still working on this. Let's do bridging methods. And our bridging methods are transparent and source route. And I'll go through both of those. So transparent bridging is actually its own protocol. It uses spanning tree protocol. And spanning tree protocol, I think, is pretty hang on, I can only do one thing at a time. I can talk or I can write, but I can't do both. Spanning tree protocol is pretty cool. Okay, so it is technically called transparent bridging. It is technically called transparent bridging, but it is spanning tree protocol. So when I say what are the two bridging methods, you could say transparent and source route, or you could say spanning tree or STP and source route. Those would both be correct. We understand that. Hang on, I moved a screen here. Can I? Oh, I don't even know what I'm clicking on now. Okay, I think I messed up something. It's still recording. You can still hear me, right? Yep, you can still hear me. Okay, just going with it. All right, so spanning tree protocol. We're just going to go through kind of a brief overview. When we get to TCP/IP class, we actually drill down into it with a lot more detail, and it actually is really cool. So the reason for spanning tree protocol is here. Let me demo why. Okay, let's say we had LAN 1, and LAN 1 we'll just say it has a hub. I'm going to do H for hub. It has a hub, and it has 3 A B and C are connected to that, and then this goes to LAN 2, and it has a hub in the middle, and D, E, and F are connected to that. And then we have LAN 3 over here with a hub, and G, H, and I are connected over here. All right. So since these are all, let me tilt that a little bit. Okay. Since these are all layer 1 devices, everything in here is layer 1. If A sends a message to B, sends a unicast message to B, not a broadcast, but a unicast, it comes down here to this hub. This hub regenerates it, and because it's layer 1 and it can't filter it, sends it out to every other interface other than the one that it came in on. So it's going to go to B and C, and it's going to go out both of these lines. It's going to come into this hub. Same thing's going to happen. It's going to flood D, E, F, and it's going to go this way. It's going to also come in here at the same time and go to G, H, and I, and it's going to go that way. And I don't know, can I draw an explosion? So at that point, we have a collision, and we lost those transmissions, and that's going to have to go again. So this is called a looped layout. And that is bad, because if you have a loop layout, you're going to lose packets. Now, I'll tell the story. We had an unintentional loop layout at one point in the lab, and what would happen was our throughput would, if this is 100% throughput normal and this is 0%, our throughput would go so it would work for about 5 seconds, and then it wouldn't work for about 3 seconds, and then it would work for about 5 seconds, and then it wouldn't work for about 3 seconds, and that went on. That took us about 2 weeks to figure that out. I'll tell that in just a little bit. Okay, so Spanning Tree Protocol, or STP, is a bridging switching protocol because it's layer 2. So it's a protocol that layer 2 devices use to communicate with each other to make sure that this mess doesn't happen. So I'm going to draw a simplified version of that and just say this is network 1 and this is network 2 and this is network 3. You know that there's, and we could say there's a switch in there. In this case, there would have to be a switch in there for Spanning Tree to work, because if there were hubs there, it wouldn't work at all. All right, so we got switches in each of these, and actually, no, let's leave hubs there. Let's leave hubs there, and let's put a switch here. So we'll say these are really long runs, and we need to have a. This simplifies things a lot if I put the switches here. All right, so we'll keep the same logistical layout there, and we'll just put switches here. All right, so since everything inside each of these circles is layer 1 and the switches are layer 2, and they're using Spanning Tree Protocol and they're communicating with each other, what they will do is they will initially elect a root bridge, kind of a king of sorts. So let's say that they have voted, and for some reason they have elected this switch the king. So what will happen is they will figure out what communication paths they need so that everybody can talk to the root bridge. And when they figure that topology out, we know that, here, let me do, because I have different colors. So we know that this one is important to get to, let's say this is switch 1, switch 2, and switch 3. So to get from switch 1 and switch 2, we have to use that path. And to get from 1 to 3, we have to use that path. But we don't need either one of these paths. We have to get to LAN 3 somehow, but we don't have to get from these two switches. So what will happen is one of these two switches will actually kill a port, and And so we'll have from this switch to this switch to this LAN, and well, this switch to this LAN to that switch to that LAN, and this switch to that LAN to that switch, and we're done. So if this switch kills that port dynamically, so in software it will just disable that port, now there is no way for us to have this horrific looped layout, because if A sends to B, just like we had before, it'll go out and it will get to LAN 1, 2, and 3. And then because this line now is dead, because it's unplugged on this side, that end is dead. So essentially this wire doesn't exist in this actual layout. There's no way for it to loop, and everything is great. And this is something that the bridges will talk to each other. Usually it's every 30 seconds, but I've seen on our network we have a lot more traffic than that. I've got 4 switches, I think, in the cabinet, and the IS has their own switch in the cabinet. One of those 4 is IS's switch, and it's really chatty. It really talks up, and when we've had some issues with that. Now, that's spanning tree protocol, and it's invisible. It's automatically enabled on devices. And if we were in the classroom, I could do a Wireshark capture, and we would see spanning tree. We would see STP. Okay, so I just I'm opening up. Nope. Come on, Wireshark is in there. There we go. You wanted to open up Bing. So here's our packet capture. We looked at this once already. I do not know. I have not looked at this ahead of time. I don't know whether I'm going to be able to see spanning tree. I do have 1, 2, 3, 4, 5, 6. That's pretty sad. I have 6 switches in my house. I had 2 in the basement, a small one and a bigger one. And then I just added that $20 one in my office. And then I've got 2 upstairs. Okay. Hang on. It opened it up on a different screen, and I can't get to it. Hang on. There it is. Whoop. Boop. Okay. So I'm hardwired. So what we're looking for under protocol here, there's TCP. We've got some UDP, some IGMP, STP, and I forget what color that's going to be. I thought it was blue. I am not seeing any STP go past SSDP, but that's not what we need. Oh, there was an STP. There's another STP. Okay, we can stop. All right. Yes. Okay. Look at that. Spanning tree for bridges. Okay, so there is a root. Okay, so spanning tree protocol. It is part of we have the frame there, LLC. So this is layer 2, so we're still at layer 2. We can see that it's a spanning tree protocol frame. It is, that's the root identifier, and the bridge, which is the root. It's identifying the port that it's talking on. It has a hello time. That's how often it's going to talk. That one is not all that exciting, but what we can do is we can filter by that. So there actually, I must have missed a lot of them. There was a lot of spanning tree. Now, it's from the source is all the same switch. So I don't know, and it's all the same, I mean, different times, but it's all the same switch, because it has, this is the MAC address of it right there, and then it's all STP, obviously, all doing the same thing. Basically, it's the same packet, and they are off, and they're coming kind of right after each other. Anyway, that is a lot of spanning trees. So one of the devices, and I don't know the MAC at. Oh wait, here's a good thing. This is tying some things together. Okay, so if I go here and I do OUI Finder, and I look this up, and I can come in here, and my source, I should, nope, can I, it is, okay, so 086060, I just gotta remember it. OUI find up, I've already forgot, 08060, 080660. 08066E. So I got an extra because I can't type with a microphone in my way. Let's make sure. 08060. Yep. That would have caused a problem. Dyslexic today. Find. Asus Tech computer. So that is my Asus access point, actually, that's doing that. So that I could go around and look at model names, or brand name, sorry, and find which one of the devices that actually is. So that's looking up the OUI actually is pretty nice. I don't have to log into every device and then pull and see what the MAC is, and a lot of them we may be hard pressed because they're not gonna. A lot of the devices won't show their MAC address on it. I'd have to actually do a little bit more interrogation of the network. So that part was nice. Okay, this really didn't tell us much. When we get into TCP/IP class, we actually start breaking this down. So one of the things you'll get in, unbelievably, and it still kind of amazes me, and I mentioned it before, that it's really cool that I will give you this entire dump, all of this hexadecimal. I won't give, well, and I might give you the whole thing because this just has garbage, but I would give you that highlighted in blue, and you would have to tell me what's going on, what kind of packet is it, and what's its source and destination MAC, and source and destination IP. But you would know that it's a spanning tree protocol, and because it's layer 2, it does not have IP address on source or destination. So but after TCP/IP class, you'd actually be able to take that hexadecimal dump by itself, break it down, and tell me that that's a spanning tree protocol, or a spanning tree packet, which I think is pretty, I think it's cool. Okay, so back to the notes. It elects a root bridge. It allows for loopless layout. I mean, that was... And you could Google spanning tree, and there are YouTube videos. If you want to know more, you only need to know what STP stands for, and that it provides a loopless layout for layer 2 bridges and switches. If you want to know more, just wait until TCP/IP class, because I think we have like half a chapter just on this, and we talk about the algorithms involved. It's Dijkstra's algorithm that it actually uses to figure out what the layout should be, and I think it's fairly interesting, and we get into it a lot. We had an issue with this. Actually, let me do source route, and then I'll go back to the issue that we had. Okay, so source route bridging is different because instead of the devices actually talking together and figuring out what's going on, source route bridging, it's kind of like if I sent you a package, but I gave like the MapQuest or Google Maps directions, and I pasted it on the outside of the box to say, hey, delivery guy, this is exactly the path that I want you to take. So normally, because this is layer 2, I can filter or not, but anything that's a broadcast is going to go everywhere, and anything at layer 1 obviously is going to go anywhere. But all I have the ability to do is pass it or filter it, and source route bridging says, I want you to go to this switch, and then I don't want you to go that way. I want you to go this way, and then I want you to go this way, and I don't want you to send it there. So it's very specific. Now, source route bridging doesn't get used very much. We almost always use spanning tree. And in fact, I can't even remember of a situation that I've had where we've used source route on anything that I've ever worked on. But source route has more overhead because the client actually has to calculate the entire path, and it can have problems because the great part about, and I didn't mention this, the great part about spanning tree is if for some reason we get somebody unplugs that cable right there and that goes down, and then we know now this switch is going to be isolated. If these guys, if they haven't heard from this switch by its timeout period, this guy will re-enable this, and then it will self-heal the network. And then if this ever gets plugged back in, then it would reorient and somebody would kill a connection to prevent the loop. At least that's how it's supposed to work. So it is pretty cool, and it's dynamic, and it recovers from bad things. Source route would not. If something got unplugged and source route said you got to go down this path, it's kind of like having just very specific directions, and you get there and the road is closed, and you're like, well, that's it. I don't know how to get there. Spanning tree protocol will allow you to get around that. Now, our story, we had an issue, and as I said, our connectivity was up and down, up and down, up and down. And this actually was really cool because Bill, who was our net admin, I think I know a lot, and I feel pretty dumb when I would talk to Bill. Bill retired last year after 30 years, but he had a photographic memory. He taught TCP/IP and advanced routing, and taught it without any notes. He would just fill the board with information. It really was. I mean, it was something. It was like learning by fire hose, though, because he had so much information and he would pump it out so quickly. But anyway, I looked at this. I knew we had this problem, so I started doing packet captures. And our packet captures, when we're looking, and if I turn that on again, we would get packet. Well, this was like packet, and then it would go up, and then we'd be getting like 100 packets a second. Then we get 1,000 packets a second, and then it would stop, and the switch would basically reboot. And then it would start, and we'd have normal packet load, and then 5 times that, and 10 times that, and 100 times that, and then it would go out. So it was just that in about 3-minute cycle, maybe, I think, total from one end to the other, if I remember right. So we're like, well, it's probably a broadcast storm. It's probably a network card that's actually cranking out too much information, and so all we have to do is look through here, and we probably should see a majority of the traffic should come from one client. Well, that wasn't the case. And then, I went and talked to Bill. Hey, there's a situation, and Bill taught in the classroom as well and used the lab as well. So, it was in his own best interest that everything worked. And I said, well, I don't know. I mean, I'm doing. So we thought, well, it's got to be one of the clients that's malfunctioned. So I went around and started shutting down individual. We have 25 PCs and 4 switches and 3 servers and 2 NASs, 3 NASs now that are connected to the network. So just one by one, I was shutting down, and I was leaving the. I did a ping-t, which we'll talk about later, which is just a continuous ping, and it would work, and then it would go out. So we could tell from that things were going out. And I was using a packet capture on one. So, we start shutting machines down, and it's still doing the same thing. We shut another machine down, wait 5 minutes, it still does it. Shut another machine down, wait 5 minutes, it still does it. So I'm like, what's going to happen? We're going to shut every machine down, and the one we're actually using to do the analysis on is going to be the one that's going to be the malfunctioning one. So we get all the way down till we only have that one left, and I'm like, see, I told you. So we fire up another one of the ones that we know isn't the problem. We move all the Wiresharking and everything over to that machine, and we shut the original machine down, and it's still going. So So, I mean, we're just like, we worked on this now for an hour or two, and it should be easy. We know that it can't be a looped layout because we're using spanning tree on our network. So we know it's not that. We can't figure out what it is. So basically, I'm individually shutting down, and this actually is kind of it was embarrassing because it's actually. In a way, it was good because it was inside Net Essentials we were talking about, and I was actually looking at these Wireshark scans on a day-to-day basis, and we're talking about what it could be and what it couldn't be and why. And Bill's talking with his advanced routing class about what the issue is and why we're, what we've done to troubleshoot it and what are the things we could do. So it was a really good real-time issue. But and someone's like, well, it's probably a loop layout. Well, it can't be because we have spanning tree, and spanning tree is taking care of that. I mean, we can see the spanning tree data that's actually on the network, so we know it's working. And after about a week of that, somebody in the lab, we have two pieces of raceway going. We've got a bottom one that actually was my original raceway that has power outlets, and it has network jacks it has power outlets and network jacks that go underneath the tables. So there's 4 headed network jacks. So I got 12 jacks coming out on each of these. And then we needed more, so I ran another set of raceway that goes along the wall that's above that actually adds 12 more in each. So we've got like 96 connections in there, and this one runs to one switch, and this one runs to another 20. We only have 24 on each one, so this runs to a 24 port switch, and all these run to a 24 port switch. And so those 24 port switches then are cross connected, so all that data is going there, and all this data is going there, and they're cross connected like that. And somebody was sitting over in the lab and said, hey, there's a black cable running out of the top and running into the bottom. Is that a problem? And I said, well, number one, it shouldn't be there. Number two, it shouldn't be a problem because spanning tree should take care of it. But go ahead and unplug it. And he unplugged it, and the network went back to normal. So we plugged it back in, and we found out that Bill had an enterprise switch in the cabinet, and then I had just some gigabit fairly cheap gigabit managed switches. Well, his big enterprise switch was running one version of spanning tree, and mine were all running a different version of spanning tree. So mine were all talking to each other and staying in communication, and his was not talking to mine. So he was sending out packets, and mine were sending out packets, and they were communicating like they were talking to each other, but they weren't. And so, yeah, this exact thing that was absolutely supposed to work using spanning tree actually died because of the enterprise level version numbers that we were using. Anyway, that was way too long a story, but spanning tree sometimes doesn't work the way it's supposed to. All right, let's keep going on this. So we did bridging methods, and we just did bridges and now switches. Same thing that we had before. When we talk about a switch, we're talking about something that is layer 2. If I'm talking, there actually are layer 3 switches and layer 4 switches. If I'm talking about a layer 3 switch, something that can see an IP address, I will say layer 3 switch. Someone else will say layer 3 switch or layer 4 switch. A layer 4 switch is just a switch that is aware of and can see IP addresses and ports. So when we say switch, we mean layer 2 MAC address switch, just like normal. And in this class, that's all we'll do. When we go to TCP/IP class, we'll start talking about the other functions. So we got a multi-port bridge, allows full utilization using full duplex. Normally it's half duplex, but we can use full duplex. Directly links individual ports. We know that allows multiple transmissions at once, and that multiple transmissions at once. Oh, Sorry. God, I keep looking at the bottom screen. All right. Functions at layer 2. Hopefully you have already downloaded. You probably should just download and print out, or at least be looking at this handout so that I don't lose you there. Functions of layer 2, blah, blah, blah. So we're actually right there. Allow multiple transmissions at once. And I promise I will do better on looking at the top screen. So what it allows me to do in this, let's say 3, 4, 5, 6, 7, 8 port, my 8-port switch there, if A wants to talk to B because of the switch knows the MAC address, it actually can, let's call that a collision domain. It actually can create a small collision domain, and A and B will actually be talking directly to each other. We're going to talk about that in a couple minutes. C and D potentially at the same exact time could have another collision domain, and so this could happen at the same time as this. Even with CSMACD and contention, the switch is going to filter that out. So the traffic from A is only going to go to this port, and the traffic from C is going to go to those 2 ports. So in this case, we actually could have 4 simultaneous conversations going on because of the way we could actually subdivide this. All right. And as I said, we're going to talk about that in just a couple minutes. Segments the network traffic by dividing collision domains into single ports. It's actually port pairs, not single ports, but close enough. Maintains a switching or bridging table, allows for filtering out things by MAC address by default. Slower than a hub because it has to actually peel open the packet to layer 2, look at the MAC address, then it has to look it up in its table, and it has to compare and see, should I pass this or should I not pass this? And as we get higher in the stack, the devices get slower and slower and more expensive, typically. All right, so the switching modes that we have are cut through and store and forward. Almost everything that we'll use is going to be cut through. A cut through switch reads just enough of the packet in so that it can read the header. It needs to be able to, if this is a switch, it needs to be able to see layer 1 and layer 2. There's really nothing in layer 1, so it reads layer 2, it sees the MAC address and topology and anything else that it needs in there, and then it can make a decision. So it doesn't have to wait until the entire packet loads. It doesn't have to do any error checking at all to see if it's all there. As soon as it gets the header and it can see the header and it's a valid header, it can make a decision and then figure out whether it's going to push stuff through. Very fast, but it actually can propagate errors. So if the header is there but half of the data is gone, it's going to push that through, and we're going to have an error. But I mean, when that happens, on the other end, we're going to get the CRC frame check sequence isn't going to work out, and then it's going to get dumped, and then layer 4 is going to come back, so it'll take care of itself. Store and forward is the opposite of that. Store and forward reads the entire data packet in, make sure everything is good, then it actually makes a decision. So it's slower, but it won't propagate errors quite as much. Typically, we're worried about fast, so we're usually cut through. And this is another thing that I did not do earlier, but let's go to Newegg, just because Newegg typically has more specs. Let's look up gigabit switches. No, I don't want that. Let's look up gigabit switches. Basically, this is going to be the same thing that we had from Amazon, but when I go to specs here, okay. Well, typically when I go to specs, it's got, okay, here it is. Nope. Let's do this 24 port. So 48 gig switching capacity. That'll come up. This is actually full duplex 24 port, so it can go gigabit in either direction. So every port can do 2 gig, and there's 24 ports, so you get 48 port. This 48 gig switching capacity is the capacity of what we would call the back plane, by the way. It has 18,000 entries in its MAC address table too, so the bridging, switching, filtering table has the ability to hold 18,000 in there. And that would be for a larger network. What we're looking for is the detailed specs. There we go. Okay, this is what I was looking for. Okay, this still isn't a very big list, but IEEE 8023, so it's Ethernet, it's unmanaged, it has 24 RJ45s at 10, 100, 1000, so it's gigabit. It is store and forward. There we go. So this, how much is it? $78 for store and forward. That's actually pretty good. So if we went down to this, let's do the same thing here. See if this has. Okay, so does it say cut through? No, it doesn't. Typically, the default is cut through. Store and forward is, I'm not seeing that in the list here, so it probably is. The cheaper ones typically are cut through. So they'll just go for fast. The more you get toward enterprise, the more you're going to pay, the more you're going to get store and forward. And that for $78, I really wasn't expecting that to be store and forward, so that was pretty good. Also able to create VLANs, virtual LANs on a managed switch typically would be the ability to break up our broadcast domains into smaller units, and I know we haven't talked about that yet, so we'll come back to that here in a second. The rule for layer 2 is because if it knows, hang on. LAN A with a hub and a bunch of machines, and LAN B, hub and a bunch of machines. We'll have a device here. We put a layer 1, we put a hub here, or a repeater. Anything sent over here goes over here because there's no filtering. Layer 1 device basically melds this into one big. So if I had A and B and I put a layer 1 device, we'll just use numbers there, and we had connections there. If someone in A sends a broadcast, it's going to go everywhere. Hang on, I'm looking for another colored pen. Okay, this is a overhead marker, but if somebody in A sends a unicast to somebody else in A, because it's all layer 1, this blue is called the collision domain. That is all the places where somebody has to shut up because CSMA CD is working and that packet has to pass. The red is called the broadcast domain, and that is where a broadcast packet will be sent to on the network. So at a layer 1, the entire everything becomes basically one gigantic LAN, and the collision domain and the broadcast domain are the same. Now, if I put a layer 2 device here, that potentially could change. So I'll draw that out, B, and I put a layer 2 device in the middle, and we have that connected. Now, if somebody in A sends a message to somebody in A, and I guess we got to back up. In order to understand this, we kind of have to walk through this. So let's say I have a hub over here, and A, B, C, and D are connected to that. And then over here, I have a hub, and E, F, G, and H are connected to that. All right. So LAN 1 and LAN 2. If I put a switch here, or a bridge, because it's only 2 port, we'll make it a bridge. So this bridge has a learning bridging table. When it first fires up, right off the bat, it doesn't know anything. And we're about to say that the rule for layer 2 is when in doubt, pass it. DOUBT, when in doubt, pass it. Okay, we'll see how that works here in just a second. So the bridge gets, let's say A is going to send something to B. The packet goes to the hub, gets sent everywhere, it comes down here. The bridge says this is coming from A to, or it's going to B. Now, it does say, oh, hey, because of that, I know where A is, but I don't know where B is. So I'm going to go ahead and pass it. So this one gets passed. All right. So then B responds. B sends back to A. So B sends to A, it comes here and it floods, so it's from B, and the switch says, hey, I know where B is, and I know that B and A are both on this side, so this one gets filtered. It will not go. Now, let's say that A sends something to G. Comes in, it knows that A is on this side, but it doesn't know where G is, so it passes it. G responds. G to A comes in, it knows that G is on this side, it knows that G is on this side now and A is on this side, so this will be a pass. This will be an intentional pass. It knows that it needs to go. Now let's say that A sends to M. M doesn't exist or is not on at the moment, so we know A is on this side, but we don't know where M is, so the rule is when in doubt, pass it. So this one's going to get passed because we don't know. We don't know. We can't filter because we don't know. And let's say A sends a broadcast. BC is always broadcast. So A sends a broadcast, which is to everybody, and broadcasts always pass. Ooh. Let's add that. Broadcasts. Whoop. I can spell, I really can. Broadcasts always pass at layer 2. All right. So this switch gets smarter as it goes, meaning that the learning table is more populated. So after, and typically the first thing that a device will do is it will try to pull an IP address, so it sends out a pure broadcast, and so that will populate this table. So E, F, G, H. So pretty quickly after the bridge turns on and the machines turn on, this is going to be fully populated. Now, at this point, if we were in back 10, A and B, this one then will be filtered. That one's going to be filtered. That one's going to pass. G to A is going to pass. A to M. Still, M is not up here, so that would pass, and the broadcast always passes. So the only difference we had is that very first packet passed because it didn't know better, but now it knows better, and it would filter it out. So what happens is on a layer 2, it passes everything. So it starts out passing everything, and it eventually gets to where it passes some of the packets. So it gets smarter and it is able to filter more. So as time goes on, but let's say we get to this point and we reset the bridge, we unplug it and plug it back in, it'll flush that bridging table and it will pass everything again, which actually we can do electronically. That's in security class. We'll talk about an ARP attack. I can actually confuse or flush this learning table, and when I do, it'll start to pass all traffic to everybody, which is one way where I could potentially see your traffic if I needed to, but that's a security class topic, which is way beyond the scope of this class. Okay, so let's go back to this. Oh, in creating VLANs, I will come back to, let me make a note here, VLANs, and I'll put, that was supposed to be a star. I've been doing this for a while today. Okay, so I put VLANs on there, and that was supposed to be a star, but it ended up being a plus, so 2 stars. I'll come back and talk about VLANs, but VLANs are basically making up additional broadcast domains. Actually, I should probably talk about that now. Okay, so on our switch, what we could do is we could set this up. By default, everything is in VLAN 0 typically. So I could set, let's just say we had these 3 ports are in VLAN 1 and these 3 ports are going to be in VLAN 2. Essentially what I've done is when I send out a broadcast, when one of these, let's say this is A, B, and C, are all 3 in VLAN 1 and D, E, and F are all in VLAN 2, I basically kind of created 2 physical switches out of this. So A to everyone as a broadcast will only go to these 3 ports, and D to everyone will only go to these 3 ports. So we're actually creating, we can still get from A to D, we can do that, but it's not acting like a router. It's doing some similar things to a router, but in this case, the definition is it's subdividing. It's creating additional broadcast domains, so it segments into virtual broadcast domains. So it makes sure the traffic doesn't go everywhere. And what we can do is this could be devices in one building. This could be devices in a different building, or I could actually have another switch over here and 6 ports, and I could have these 2 could be in 1 and these could be in 2, and then I could have a third VLAN there. So if somebody over here sends out a broadcast, it actually goes across, there's a VLAN trunking protocol that actually gets used. So the packet would actually be sent to both of the, well, I would start with here. It would be sent to this port. It would be trunked across and sent to these 3 ports as well, but none of these ports would get it and none of those ports would get it. Same thing if something was sent over here and it was a broadcast in 2, it would be trunked across and it would go to those 2 ports. So it allows us some additional configuration. Cheaper switches are not going to have VLAN control. That $78 one probably had VLANs on it, but it would have to be semi-managed to be able to do that. My little $20 gigabit switch does not have VLANs, but I mean, it's only, I don't need VLANs. It's 5-port gigabit switch. Okay, so rule was when in doubt, pass it. We go to layer 3 in routers. Oh, and I'm coming up on an hour. All right. I'm going to break here just because we're about in an hour, and then I'm going to continue this on part 2. So I'll see you in a minute.